Kia ora koutou, thank you for having us. We are here today to share a little bit of our journey creating a Kubernetes platform service, both for the Catalyst public cloud in New Zealand, but also for OpenStack upstream. So for those of you that don't know us yet, just a little bit of background to get us all on the same page and in the right mindset for this presentation. We are a public cloud provider with 3 regions in New Zealand. And more recently, a lot of New Zealand large enterprises started coming to us and saying, can you please build us a private cloud using the same technologies that you use for your public cloud and manage this for us, right? A lot of them are on that Kubernetes journey where ultimately they want to get to Kubernetes, but they are mindful that they need an infrastructure as a service layer that is fully software defined, and that's where OpenStack comes in. In October last year, we launched a service in alpha on the Catalyst Cloud that became New Zealand's first certified, CNCF certified Kubernetes platform in New Zealand. And more recently, a couple of months ago, Long, I think? In June, end of June, we became a Kubernetes certified service provider, right? And that's because we've been contributing quite heavily to this project called Openstack Magnum. Now, if you're not familiar with OpenStack, imagine it as a cloud operating system that you install on your data center. It controls everything that is happening inside the data center and exposes all those things as APIs that you can use to interact with those services. And Magnum is the container orchestration engine provisioning service. That's a mouthful to say it deploys Kubernetes clusters, right? Not only Kubernetes, actually it also deploys Docker Swarm and Apache Mesos. But most of the customers we interact with are settling down on Kubernetes, and especially on the Catalyst public cloud, we're focusing on Kubernetes. As you can imagine, a little bit like the Google Container Engine, it's something that will allow you to go into OpenStack and say, I would like a Kubernetes cluster. How many worker nodes do I want? How big you want each worker node to be? And it goes and provisions and manages the cluster for you. But this is the Cloud Native Summit, so I don't expect you guys to be using a dashboard and clicking buttons to deploy a Kubernetes cluster. That's what you would be doing, for example, if you are using Terraform to deploy a Kubernetes cluster using OpenStack Magnum, right? So it can be as simple as the name of the cluster, the SSH key that will have access to the worker nodes, how many worker nodes, how many master nodes, and the size for each one, and that's it. Now, let's talk about the journey and where we begin. Our high-level requirements when we created this service for the public cloud or started contributing upstream on it were strong security. On the security side, we knew there was a new version of Kubernetes coming up every 3 months, right? So first and foremost, we need to keep on rolling forward. Secondly, it's a still bleeding edge technology. There are critical vulnerabilities every now and then. We'll need to be able to patch this, and we'll need to be able to patch this without downtime for the applications. Then most organizations have an identity and access management solution, and they would like Kubernetes to hook back into their identity and access management solution. We're not different. And network policies. We wanted to be sure that we could filter traffic between pods inside Kubernetes. Then on the high availability and resiliency side, excuse me, we wanted the master nodes to be highly available, but we also wanted to be able to detect any failures within the cluster and to recover from these failures automatically. On the performance side, we wanted to benefit from the raw performance we were getting from the OpenStack software-defined networking, from the software-defined block storage service, and more importantly, we wanted to have some horizontal scalability. So if you're running out of resources on your Kubernetes cluster, we wanted Kubernetes to be able to say, hey, I cannot schedule pods anymore. Can I please have another worker node? And so long you are inside that min and max number that you define when you create the cluster, that you keep on expanding the size of the cluster. And finally, we wanted it all to be easy to use. And for us, that meant out-of-the-box integration with the infrastructure as a service layer, and also being able to use it via Terraform and Ansible modules. So let's look at the design and the implementation, starting with software deployment. And apologies if I'm turning around a little bit. I don't have a feedback monitor here, so sometimes I'll turn my back to some of you. Apologies for that. On the software deployment side, if you look at typical Kubernetes master node, right, where you have your kube API, your kube scheduler, controller manager running, what we do with OpenStack is to run a virtual machine that has Fedora Atomic as the base operating system. Fedora Atomic is a Linux distribution optimized to run containers. So when you look at it, you see the kernel, the Docker engine, systemd, and rpm-ostree, right? It's quite a stripped down version of Linux. That made it excellent for this purpose, super lightweight, and also hardened, so really good for this use case. Then we had to produce a CI/CD pipeline because each one of these components that you see in there, the kube API, the kube scheduler, they're actually being deployed as containers. So we had to produce a CI/CD pipeline that would produce these container images for us and also test them to ensure they pass the CNCF tests for the certification. Which, by the way, I learned yesterday that there is a company in New Zealand called Hippie Hacker who actually produces the Sonoboy tests upstream together with Hep2 for CNCF. And I didn't realize it was a New Zealand company. Very happy to see other people doing this sort of contribution in New Zealand. So the containers are, they are managed by systemd inside the host. And because of that, this whole thing is quite easy to patch and upgrade. We could patch and upgrade the operating system or the kernel version by doing an rpm-ostree command, but we can also as easily just rebuild the whole node by doing, say, an OpenStack Nova rebuild command, because it's all ephemeral to some extent what's going on inside the cluster, right? The only data that you have being persistent on disk is the etcg cluster, and that's on a separate block storage volume. So ultimately, when you're deploying a Kubernetes cluster, you will end up with multiple master nodes and multiple worker nodes. The question is, how do we put it all together? How do we integrate those things and deploy a cluster? And there is a service in OpenStack called Openstack Heat. And Heat is, in the Catalyst Public Cloud, we call it the container orchestration, the cloud orchestration service. And for those of you that are familiar with Amazon, that would be equivalent to your CloudFormation on Amazon, right? So ultimately, something that allows you to describe or create an application template that describes all the resources you need to deploy an application. You could say, I need a network, I need multiple servers, security groups, floating IPs, block storage volumes. And what it does is it produces this graph highlighting the dependencies, and it will navigate this graph and issue all the API calls on your behalf to provision both the infrastructure resources, but also to do the software configuration inside these resources, like deploying those containers that we've seen in the previous slide. So now that we have a running cluster, let's jump into the configuration of Kubernetes itself, right? One of the things we've learned is that we need to hook that back into our identity and access management system. And in our case, the service in OpenStack is called OpenStack Keystone. And what we've done is we developed this webhook that will do authentication with Keystone by either fetching or accepting a Fernet token. And Fernet tokens were created by Heroku, I believe, and they are akin to JWT, if you're familiar with JWT. On the roles side, we created some roles in Keystone for Kubernetes, Kubernetes admin, for the admin of the cluster, developer, and viewer. But what we've done is we left these roles empty with no policy associated with them. And that's because the actual authorization side is done in Kubernetes using RBAC. We have pre-populated the RBAC controls in Kubernetes with what we believe are sensible defaults for this role. But what we have learned is that a lot of people want to customize those roles and actually say, hey, for my viewer role, I would like to add this one more thing or remove this, right? So you can actually customize that inside Kubernetes using config maps. And we thought that that was quite flexible. On the network side, so when it comes to pod-to-pod networking, Kubernetes only cares about three things, right? So long you meet these three rules, Kubernetes is happy. First one is containers can communicate with each other without net. The second one is nodes can communicate with containers and vice versa without mesh. And the third one is the IP that a container sees itself is the same IP that others will see it as. So long you meet these three rules, Kubernetes will be quite happy. So in our case, we have looked at a bunch of options, different Cni drivers for Kubernetes, and ultimately we settled on using Calico as our Cni driver for two reasons. One of them was performance and simplicity. Well, that's three reasons then. Performance, simplicity, and I guess the other one was security because it does the policy enforcement and the network filtering. In a nutshell, the way Calico works is inside each pod in green, you can see that inside each worker node in green, you can see that they have private network in there. And what Calico is doing is to deploy an agent in the bird routing daemon to each one of the worker nodes. And it's establishing this BGP mesh just to exchange routing prefixes between the worker nodes. So if a pod on worker node 1 wants to talk to pod on worker node 2, it will drop that packet on that subnet because it's not destined to someone in that same subnet. It will go to the default. There is some routing rules that Calico injects in the default network namespace there, and that will pretty much just drop the packet on the software-defined networking under the hood, and then go to worker 2 and reach that pod, right? So it's quite simple. It's quite simple to understand, and it's quite simple to manage, and it delivered really good performance for us. Now, the next step is you have Kubernetes up and running, identity and access management is sorted, networking sorted, what else, right? Well, let's say you wanted a persistent volume in Kubernetes, or let's say you wanted a load balancer. So we needed to integrate Kubernetes to the underlying infrastructure as a service layer so Kubernetes could obtain these resources. And the way you do this, if you're running Kubernetes on top of a private or public cloud, is through something called cloud providers. So Lingchen, who works with Fei Long and myself, is a big contributor on the OpenStack cloud provider upstream. And some of the things we've done, for example, is to extend the OpenStack cloud provider to support the OpenStack load balancer service, Octavia, so that if you're deploying a service with type load balancer, or if you're creating an ingress, it can actually talk to that API and fetch a load balancer on your behalf. Or that was already built in. If you want a persistent volume backed by one of the block storage types that you have in OpenStack, it will talk to OpenStack Cinder and fetch that volume for you. So ultimately, now we are looking at the cluster. You have the master and the worker nodes, but these boxes inside are now pods that have been deployed in there. The ones that are inside the nodes are actually daemon sets, and the ones that are outside are just regular deployments. So I just want to show you what the cluster looks like on the inside. On the top there, other than Calico, you have the Kubernetes Keystone Auth. That's the integration with the authentication system. Then you have the OpenStack Cloud Controller. That's what will pick up the requests for persistent volumes and load balancers. And there is this new component that Fei Long and Lingchen developed upstream called the Magnum Auto Healer, which I've learned yesterday is useful not only for OpenStack, but it could be useful in other deployments as well. And Fei Long will talk more about that later and how it works. I just want to point out one component that we have here called the, there you go, the cluster autoscaler. That is the component that is monitoring Kubernetes and looking for any deployments that are in a pending state because you don't have enough capacity to deploy. And once it sees that, it will check the min and maximum number of worker nodes that you have for that cluster and fetch an additional worker node if you're running out of resources, right? So I will hand over to Fei Long and let him talk a little bit more about the ongoing management of these clusters.
So Bruno has pretty much covered some our journey, how we design and implement our Kubernetes service. For my part, the first thing I would like to mention, to highlight, is all our work is open sourced. You can find it on GitHub, Openstack Magnum, all open sourced. And for my part, I will cover two typical scenarios when you do the ongoing management for the Kubernetes cluster life cycle. The first thing is rolling upgrade. So currently, Kubernetes will release a new version for every 3 months. It's quite frequent, you know. It's painful. Yeah, it's really painful. So the thing we would like to do is we would like to support like an API, a command, just one click to upgrade from one version to another one. So as you can see currently in OpenStack, you can use the command OpenStack COE cluster upgrade to give your current cluster ID and then the new cluster template ID to upgrade your current cluster to the new template. With the new template, you can define the new Kubernetes version and, for example, even the image ID to upgrade to another image. And as for the upgrade process, actually, is under the hood is pretty straightforward. You just need to firstly harden your node and drain your node, then upgrade your Kubernetes components container. As Bruno mentioned, currently we're using Fedora Atomic, so all of those Kubernetes components are running as a container. So you just need to download the new container image and replace the current one. And then the final step is just unharden your current node, then all done. But the tricky thing is, the hard part is, how can you achieve a zero downtime upgrade? When I say zero downtime, it means there is no downtime for the service, the user, the customer service running on the Kubernetes cluster. So for that part, that's the thing we can do from a cloud provider perspective. We can do harden, drain, upgrade, and unharden. But from the user perspective, you still have very little things to do to get a zero downtime upgrade. The first thing, you need to make sure better to run your application as under a controller, for example, a deployment, and better have more than one replicas for your service. And the other thing, you need to make sure, better to make sure, to use the pod disruption badges. So I will explain later with a picture how that is important for your application to get a zero downtime. And another thing is you need to make sure your application can do a gracefully shutting down. So for example, if you're running Nginx application, Nginx can't accept the term signal, so they can't do gracefully shutting down. So you need to use the pre-stop hook to sleep like user has been Nginx quit your Nginx application gracefully, but that's still not good enough. Generally, you still need a sleep time to make sure when the control plan, the Kubernetes control plan, send the notification to your node, to the kubelet, to drain the node. Before that, there's still a very little chance the load balancer of your service is getting traffic from the user. So better to use a period like a sleep or something like that to get really gracefully shutting down for your application. And this picture is showing why we do need the pod disruption badges. So for example, I have 3 worker nodes, and I have upgrade one by one for node 1 and node 2, and I'm going to upgrade the 3rd one. But there is a situation that your application has 3 pods, the Nginx has 3 pods, and all the 3 pods the new pods has been launched on finally the last old nodes. And then if you just try to upgrade the current one to drain it, you still risk a situation that end up with all the 3 pods just being drained, and you still get a downtime for your application. So that's why we still need the pod disruption badge to make sure there is a minimum available, you can set it 1 or 2, whatever you want, to make sure as a minimum you still have 1 pod can get the traffic. So that's the thing under the hood, how you can get zero downtime upgrade, rolling upgrade. And another scenarios is Autoscaler. So sometimes your Kubernetes cluster still get a chance to just getting down. Your Kubernetes just down for some reasons, and you need to get it, back to the original status.
We have the video for that one, Philon. He can kick off.
Okay, cool. Yeah. As this video, we have three master, 3 worker cluster, Kubernetes cluster. So the first terminal just lists all the nodes under the Kubernetes cluster. And the second one currently, you can list all the node status is ready. And for the third one, we're trying to deploy the Magnum Autoscaler on that cluster.
Just for clarity, when we were recording this video, the Magnum Autoscaler was not part of OpenStack Upstream, so you still had to deploy it to the cluster. But now it will come baked in the template itself.
Yeah,
so
it'll be out of the box, just use it.
So that step can be skipped.
Yeah. So when the Autoscaler running, it will periodically check the health status for each node, including the master node and the worker node, and you can define the policy and the check period. And for the third window, we just use the system control to stop one of the kubelet. So as you can see, the status is getting to not ready. And then the Autoscaler will try to coordinate and drainage, and then it will be replaced with a new node. So you can see here. Yeah, it has been replaced. It's losing because it has been removed by Openstack Heat. It's trying to replace with a new one. As you can see, it's the new one. It's back to ready. So this is the whole process. And for the Autoscaler, it's also open sourced, fully open sourced, and currently we have a driver for OpenStack, but you can extend it to add, for example, the EKS as a driver or AKS as a driver. But you don't need a Google Cloud driver because Google Cloud does support the auto repair as well. And there's some predefined failure detection policy. As I mentioned, you can detect the failure for worker node, master node, whatever you want. Just define your policy. And yeah, that's pretty much. And you can find that's the link currently is under the Kubernetes cloud provider OpenStack. You can find the source code. And yeah, we still need some steps to go to the next journey. And the roadmap pretty much for the first one, we would like to provide the option to select the volume type for etcd and your root disk. For example, currently we're probably using the NVMe as the default volume type to get very good performance. And the next one, we would like to expose more the features we just mentioned because there are still some features currently only command line support. And the third one is we would like to get all the master nodes running on another, like a root Kubernetes cluster, so you can save the cost. But you can still select you want a virtual machine master or a container master, just based on your option. And the next one is operating system patching with zero downtime. As I mentioned, currently you can do the operating system patching with specify a new image ID, but there is still very little chance to introduce downtime for the application running on the Kubernetes cluster. So currently, we're still working on with the community to get a zero downtime operating system patching. And the third one is upgrade from the current Fedora Atomic images to Fedora CoreOS. But currently, the Fedora CoreOS is still for preview testing. So we are working with the community to test that. Yeah. That pretty much, yeah, what we are working.
So we have no time for questions, Craig?
Do we have time?
Really? Okay.
2 minutes or 2 questions?
2 questions.
Okay, good.
Any questions from you guys? Or I can repeat if you prefer. Everett, the man with the questions, all the questions. Yeah.
First statement, thank you for providing the Kubernetes clusters for the Istio workshop yesterday. So thank you to you personally and Catalyst Cloud. That was a great save.
Yeah.
Thanks a lot. And my question is, on your Fedora Atomic hosts, are you using Docker under the hood or Cloudman under the hood?
Docker.
Docker.
Yeah.
Docker under the hood. Yep.
Are you planning to transition as, I think, Fedora CoreOS transitions, I think?
Yeah. We're working on that.
Any other? Shannon is smiling. He's got a gazillion questions, but he doesn't want to ask. Right, one more day.
How do you get zero downtime with your ingress point? So are you using HA proxy or F5 or?
So is the question, how do we get zero downtime with the ingress support? Yeah. And are you talking about zero downtime from the perspective that the ingress or whatever load balance is fulfilling the ingress might need to some patching as well? Is that
correct? Yeah.
In OpenStack, there is a load balancing service called Octavia. And the way Octavia works is very similar to the Elastic Load Balancer on Amazon. So when you ask for a load balancer to be created, it's actually provisioning at least 2 virtual machines behind the scenes in a tenant, in an account that you don't have access to. And it's installing HA proxy in those compute instances. And it sets up a cluster using Keep Alive G. And it takes the VIP, the virtual IP of the cluster, and it puts that on a port on your own account and tenant network where you have requested the load balancer, right? So the patching and management of the load balancer is our responsibility as a cloud provider. And whenever there is a security update to HA proxy, what we do is to produce a new image for our HA proxy-based load balancer. It goes through our CI/CD pipeline, and once we know it's working as expected, we publish that as a new image in the imaging service in OpenStack called Glance. And at that point, as cloud admins, we have a single command that we run that would patch one of the sides of your load balancer and then the other, and it does a rolling upgrade of the load balancer itself. So because the Kubernetes service is using that to fulfill service-type load balancer or ingress, you end up getting no downtime when we are patching the load balancers themselves. Now, with some of the customers that we are working for private clouds, they do have F5 load balancers, but ultimately they are all pretty much asking, can you guys please implement software-defined networking and software-defined load balancing and storage for us? So we have that capability. So, yeah. Does that answer the question?
Well, to keep alive date, how does that actually, like, when it changes the IP address to the other side?
It doesn't change the IP address to the other side. You have the VIP.
When that floats to the other side, how do you not lose traffic when that happens?
So, if you have sessions, so if you have sessions that are going through one of the legs of your load balancer, in HA proxy, we can also drain wait for the connections to be drained from that load balancer. So with the Octavia load balancing service in OpenStack, one of the actions you can do is to ask for sessions in traffic to be drained from one load balancer so it goes to the other load balancer. All right. Thank you for having us.